Okay, now we'll start discussing backpropagation. But before we do that, let's quickly revise the formulas for forward propagation in neural networks. We saw last time the shapes of the different vectors, matrices, elements involved in forward propagation. We saw that A0, which is the input layer, consists of n examples of dimensions n0 or d. W1, which is the weight matrix for the first layer, has the dimensions of n1 cross n0. So you always see that the dimensions are the number of nodes in the current layer times the number of nodes in the previous layer. The bias term is containing the number of elements in that particular layer. And we also saw that we broadcast or we create a capital B1 or capital BL for the LH layer term, which consists of writing this B1 term, small B1 terms, transposing it and writing it n times for n examples. So all of these calculations are valid for n samples instead of just one sample at a time. Then we calculate the Z1 term, which is of the dimension n cross n1. So if you see that all of the terms that we'll be computing going forward will have n number of examples corresponding to each. We'll have the number of elements compared based on the number of items or number of nodes in that particular layer, which is n1 for layer 1. And we can further write this down as z1 equal to a0 times w1 transpose plus b1, and we can then write a1 as the activation of z1. So a1 is g times g function applied over z1. In general, we saw that we can write in the following way, where zl for the LH layer is al minus 1, the previous activation, multiplied by the transpose of the weight matrix for the current layer plus the bias matrix, and the activation of the current layer is the activation function applied over the z term for the current layer. We worked out an example for XOR for multiple examples. We saw that for the XOR problem we have 4 examples and 9 parameters. And now we come to the discussion on learning parameters for the neural networks. We have previously seen that using forward propagation we are trying to predict based on the current set of parameters, right? You have some weight values, some weight matrices. Based on that you're trying to make a prediction y hat. But as we've seen earlier in linear regression and when we applied gradient descent there, we have to change the weights in order to improve the objective. So that's the whole premise, or that's the whole way in which gradient descent based approaches work. So we have a backward propagation step where we go from the final output, predicted output y hat, and we keep on making changes going backwards. While predicting, we keep on going forward. Let's say we start with the inputs. We then apply these set of weights. So we apply A0 W1 transpose plus B1, we get Z1, then we can get A1. We apply the same thing for the next layer, so on and so forth. But in backward propagation, we start from the final prediction. We compute the loss and then we move backwards in order to change or improve the weights. So for learning the parameters, let's assume a few things. Let's assume that the input is capital X, as we've been using thus far. It's a n cross n0 dimensional matrix. So n examples, n0 dimensional, and the output is y hat. The ground truth is y. So both of them are n dimensional. We can then write the loss as the average loss over each of these n examples, right? So 1 over n summation 1 equal to I equal to 1 through n, the loss function applied to y hat of I, which is the prediction for the ith example, and y of I. Now this could be your mean absolute error or mean squared error or something on that lines, right? And the set of parameters theta which we want to optimize are w1, b1, w2, b2, so on and so forth, right? The way in which we apply gradient descent is as before, we first initialize the parameters randomly, and then till convergence we apply the gradient update to each of the parameters. For example, I've shown the gradient update rule for W1. So we can write W1 as W1 minus alpha. Here alpha is the learning rate of the step size, times the gradient of the loss with respect to the parameter that we concerned, right? So the loss is j theta, which is computed over here, and we compute the gradient of that loss with respect to the variable of concern, which is W1. Now, of course, the important question here is that how do we compute the gradient of the loss with respect to the weight matrix that we're concerned with, and the rules of calculus remain the same as we've been using earlier, like we were using in the case of linear regression, etc. They'll remain the same, but we'll see that they'll get a little more complicated because now we're dealing with higher order tensors. So we can also create a computation graph to make our lives easier for understanding the backpropagation and associated calculations. We just discussed this a couple of minutes back, that this is the steps 1, 2, 3, 4 are telling you the direction in which you propagate forwards. When you have to make a prediction, you start with A0, you multiply that with W1 transpose plus B1, you get Z1, you apply the activation on Z1 and you get A1. You apply this transform to A1 and you get Z2, and you apply a nonlinear activation on A2 to get Z2. You can also represent this entire thing via this computation graph. So there is one node Z1 which depends on A0, W1, B1, and the node A1 depends on Z1. The node Z2 depends on W2, B2, and A1, and A2 depends on the node Z2. Finally, there is a term which is computing the loss. The loss depends on A2, which is also the same as Y hat, and the ground truth Y. So based on all of these, we can do the forward pass and compute the loss. Now let's take some assumptions, make some assumptions about some of these functions and the specific activation functions, and try and compute the gradient rules or the gradient update rules for a particular class of problem. So let's for a particular example, let's say we'll be doing this for the XOR problem only, and we'll see that in the notebook in a few minutes from now. We'll assume that the activation function G1 and G2 that we apply. So again, square bracket 1 means for layer 1, square bracket 2 means for layer 2, and we've assumed that both of these are sigmoid functions. For the loss, we have assumed it to be cross entropy loss. Now we could trivially assume it to be cross entropy loss because we are discussing about the 0-1 classification sort of setting for XOR. You could have chosen the regression type losses or the mean squared loss, etc., and you can do all of the derivations. But for the purposes of this lecture, we'll be sticking to the cross entropy loss. So the question that we're trying to then answer is that what is the loss, which is a function of the parameters theta with respect to one of the parameter W1. So theta consists of W1, capital B1, W2, and capital B2, and we're trying to compute the derivative or the gradient of the loss with respect to one of the parameters W1. We're trying to, for that we'll also need to compute many of the other gradient terms with respect to, let's say, A2, Z2, A1, Z1, and we'll just see how all of these quantities are computed. Before that, we should know the derivatives of some of the activation functions that we'll be using. These are fairly simple to calculate. Let's say if you have the Relu activation where the functional form is gz equal to z if z is greater than 0, it's 0 if z is less than 0, and it is undefined otherwise. For the purposes of simplicity, and we'll assume that the implementations that you use will allow you to, or you have sufficient control so that you can just define gz as z when z is greater than equal to 0, or 0 if z is less than 0, or vice versa. You can choose the sign of equality in either of the two terms, and we can then compute g dash z or g prime z, which indicates the derivative, and that is 1 when z is greater than equal to 0, and it is 0 otherwise because it's a constant if z is less than 0, right? For the Leaky Relu, the functional form is fairly similar. The only difference being that gz is alpha z, where alpha is a small number when z is less than 0. And we also can write this just to make our life simpler as gz is z when z is greater than equal to 0, or alpha z when z is less than 0. And if we compute the gradient with respect to z, it is 1 when z is greater than 0, and it is alpha when z is less than 0. These were the trivial cases. Now I would request you to take a moment in your notebook and try to compute the gradient with respect to the sigmoid and the tanh activation functions. You may pause the video, go back to the previous video or your notes and revise the formula, and then try and compute the gradient with respect to these. Okay, assuming you already paused the video and did that calculation, I'll go ahead. The functional form of sigmoid is gz equal to 1 over 1 plus e to the power minus z. So g prime of z, the way I write this is as, so just consider this entire thing as some quantity. Let's say this is x. So you're firstly computing the gradient with respect to 1 over x, or x to power minus 1. So that is minus 1 over x square, and then you do del x by del z, right? So minus 1 over 1 plus e to the power minus z the whole square times d by dz of this term 1 plus e to the power minus z, which turns out to be e to the power minus z over 1 plus e to the power minus z the whole square. And one of the goals of many times what you want to do is to write g dash z in terms of gz. That just simplifies the whole thing, because then you have to just define gz, and you can in the same function write its derivative in the form of gz itself. So we add and subtract 1 over here, and adding 1 gives us 1 plus e to the power minus z divided by 1 plus e to the power minus z whole square, which is gz itself. So gz minus 1 over so minus gz square, and you can just write this as g prime z is equal to gz times 1 minus gz. You can do the same thing for the tanh activation function, where gz is e to the power z minus e to the power minus z divided by e to the power z plus e to the power minus z, and we can write this as u over v, and we can apply the rule of when you have u over v kind of expressions and you're computing the gradients. So g prime of z can be written as v du by dz minus u dv by dz divided by v square, and I've done the calculation, and if you work it out yourselves, you'll see that this turns out to be 1 minus gz the whole square. This is also convenient because we've now been able to do the derivative with respect to gz, and its functional form is also in terms of gz. Just to summarize, for Relu g dash z is 1 if z is greater than or equal to 0, or 0 z less than 0. Similarly for Leaky Relu, only this 0 is replaced by alpha. For sigmoid, g prime of z is gz into 1 minus gz, and for tanh it is 1 minus gz the whole square, right? Okay, we revisit now the computation graph, and so we notice that we had capital N examples, right? So we could have now written the cross entropy loss in the following format. But the one thing you need to think about A2 and Y is that both of them will have the same shapes. N rows, 1 column, right? So they are both elements in Rn, and when you're trying to compute the loss, you compute it in the following form. So if you see, this is the cross entropy loss form, and you carry out the summation over the n examples. So minus y circular bracket I means the ith example, and y of I means the ground truth for the ith example, and a square bracket 2 means just y hat, because a2 is just y hat and I means ith example, and you similarly have the second part of the term. Since we're trying to make things convenient for us, it would be useful if we can think of how can we write this expression in the vector form. So take a minute and try to write this in the form of y transpose or a2 transpose, this entire expression, and then we can take this forward. Okay, assuming you have already written this thing in the vector form. So y was an n cross 1 matrix. Y transpose is a 1 cross n 1 cross n dimensional matrix, and this function that we have applied logarithmic of a2 is applied element wise. So what element wise means is, you think of it as you've written the vector a2. Now the vector a2 is n samples, so it's an n dimensional vector, and you apply logarithmic on each of these. So logarithmic of the first term of the vector, logarithmic of the second term, so on and so forth. And if you do the matrix multiplication of minus y transpose logarithmic applied element wise, then you'll get the first term, and then there is a minus 1 minus y the whole transpose. Now y, the term y is a n cross 1 matrix, if you know, or it's an n dimensional vector, but 1 is a scalar. So this is sort of misleading because this 1 is not a scalar in the true sense. This 1 is a vector of all ones of shape n cross 1, and you do the transpose of this, and then again this term 1 minus a2. So here also the 1 term is an n cross 1 dimensional vector, and then again the logarithmic that is applied is applied element wise. So this is the vectorial way of writing the loss function. And the question that you are trying to see is that what is the loss of what is the gradient of the loss with respect to the parameter a2. So a2 appears here, right? So that's what we're trying to calculate the loss with respect to. To make things simple for us, we'll first write we'll break down this term into two terms, q and r, and we'll write q to be y transpose logarithmic of a2. And if we were to just expand this out just to make things easier for computing the gradient, we would have written q to be y1 times logarithmic of a21. So if you go back, this entire thing is a scalar, right? So if you see that y1 times log a2 the first sample minus y2 log a22, so on and so forth. So this entire thing is essentially a scalar and can be written in this format. And we can then compute the gradient of q, which is a scalar, with respect to a2, which is a vector. So this vector dimension is n cross 1. And earlier in the first half of the semester, we have already seen this, how to compute the gradient of a scalar with respect to a vector. We compute the gradient with respect to each component of the vector. So this expression of del q by del a2 can be written as del by del a2, the first term of it, evaluated over the entire expression q, y1 log a2 1 plus so on and so forth. But the only term containing del a2 1 is the first term, which is y1. And for this term, if you compute the gradient, you will see y1, and then you compute the gradient with respect to log of a2 1 with respect to a2 1, which would just be 1 over a2 1. So the first row corresponds to is calculated as y1 over a21. If you keep on continuing this set of calculations for all the n examples, this will turn out to be a vector containing of the following format. So yn divided by a2n. In essence, what this computes is, in essence, how we can write this more conveniently is del q by del a2, which is now a n cross 1 dimensional vector, is y. So this y element wise divided by a2, right? So each element of y, or the ground truth, is divided by each element of the prediction a2, right? You have n elements in both of them, and this symbol is for the element wise division. Now let's try and repeat the same thing for the second term in the expression. The second term was r equal to 1 minus y transpose logarithmic of 1 minus a2, and you can again expand this whole thing out in the similar format and compute the gradient with respect to a2. And then again you see for this the first row, the only term that would contain a21 would be the first term in this expression for r, and you compute the gradient with respect to this, and you will get the gradient as 1 minus y1 divided by 1 minus a2, and then and then a minus 1. And if you just try to write this entire thing again vectorially as we did previously, so you can see that there is a minus 1 term times 1 minus y1 element wise divided by 1 minus a2, right? So this is again conveniently written in this format, and now using both of these we can write the gradient with respect to of q with respect to a2, since we decomposed q and we decomposed L in terms of q and r. So thus we can write the gradient of the loss with respect to a2 as minus y element wise divided by a2 plus 1 minus y element wise divided by 1 minus a2. Okay, so far so good. We have been able to compute the gradient with respect to a2. Now so our ultimate goal is to be able to compute the gradients with respect to the weights w1 b1 w2 b2. As you can see, now we first computing the gradient with respect to a2. Next we can compute the gradient with respect to z2, and then we can get the gradients computed for w2 b2, and then we can keep going backwards, right? So one thing which we can do for these computation is to apply something known as the chain rule, which in which we can write del L, or the gradient with respect to the loss, the gradient of the loss with respect to z2 as the gradient of the loss with respect to a2 times the gradient of a2 with respect to z2. So the easy way to remember this is that if you look at these diagonal terms, they'll be the same, and then what you're left with is del L by del z2, right? So that's the idea, that if we can write it in this way, we can make use of the already computed result, because we've already computed del L by del A2, and now if you can compute del A2 with respect to del Z2, then we can compute the term del L by del Z2. And to do this, we just expand this out. We already know what is A2, right? So A2 we know is G2 function applied over Z2, right? So we can write this entire term of del L by Z2 as del L by del A2 already computed times del A2 divided by del Z2, but A2 can be written as G2 of Z2. So del by del Z2 of G2 function of Z2, which can be written as del L by del A2, already known. And if you remember, the differentiation with respect to the sigmoid was gz into 1 minus gz. So where z is the specific input. So if I just go back and show you the formula. if z is an input to a sigmoid, g prime z is gz times 1 minus gz. So we can make use of this same expression and then write del L by del Z2 as del L by del A2 times GZ2. So GZ2 times 1 minus GZ2. So all of this is easy for us because we know the functional form of the activation function, which in this case is the sigmoid. And then we can just expand this out. So del L by del A2 times gz2 multiplied by 1 minus g of z2, and we can then eventually write this as del L by del A2 and element wise multiplied by A2 and element wise multiplied by 1 minus A2. You can also look at all the dimensions and you can sort of agree with the fact that why we need an element wise multiplication over here, and we'll gradually see that why these element wise multiplication come into the picture when we look at generalized Jacobians or generalized tensor to tensor gradient computation. And we can then substitute this term, which was minus y element wise divided by a2 plus 1 minus y element wise divided by 1 minus a2, and this entire thing is now element wise multiplied by a2, element wise multiplied by 1 minus a2, right? Now we can just expand these terms as follows. So minus y element wise divided by a2, element wise multiplied with a2, and element wise multiplied by 1 minus a2, right? So at this point your element wise dividing by a2 and element wise multiplying by a2, both of them will just get cancelled out or multiply to give you 1. Thus this LHS term just finishes at minus y element wise multiplied by 1 minus a2. For the right hand side term you have 1 minus y element wise divided by 1 minus a2, element wise multiplied by a2, element wise multiplied by 1 minus a2. Now again 1 minus a2 is element wise divided here and element wise multiplied here, so both of them will get cancelled and instead we'll only be left with 1 minus y element wise multiplied with a2, which if we just compute and complete the calculations, so minus y plus y element multiplied by a2 plus a2 minus y element wise multiplied by a2, so y element wise multiplied by a2 and minus y element wise multiplied by a2 will get cancelled, and the final thing that we'll be left with is a2 minus y. So thus we can write that once we do the entire calculation, we can write that del L by del Z2 is A2 minus Y. So another way to just confirm what you've done is L is a scalar, Z2 is of dimension, what is it? So is it N2 cross N1? Is that true? Z2, let's see, what is the dimension of Z2? So Z2 is what you've predicted for n examples and the number of nodes in the uh, second layer. So the number of nodes in the second layer is n2. So Z2 is n cross n2. Okay, right. So Z2 was n cross n2 and n2 was 1 because you have only a single output node in the second layer. So thus both of these are n cross 1 and n cross 1. Thus these computation makes sense. Taking the same calculation forward, we can also then calculate the gradient with respect of the loss with respect to W2. I would want you to take a couple of minutes, look at what I've already written on the slide, take this forward, and then try to compute the gradient with respect to W2. Okay, I'm assuming you took a pause, thought about this. The first thing that we see here is that we can again write del L by del W2 using the chain rule. We have already computed del L by del Z2, right? So we can write del L by del W2 as del L by del Z2 times del Z2 by del W2, right? Now, again, if you look at the dimensions of L, loss is scalar, W2 is of the dimension n2 cross n1, and you'll see that as we go about discussing the generalized Jacobian soon, that these dimensions should match up. So the dimension of del L by del W2, since L is a scalar, should match the dimensions of W2, which is n2 cross n1. Okay, so now I would say is what is probably some optional content. It is fairly advanced, and if you master this, you should be able to solve a lot of multivariate calculus problems and similar things for a lot of neural network like problems. But as I mentioned again, it's sort of optional. So we've mostly been talking thus far about gradients. So gradients sort of look at you're trying to compute the gradient of a scalar with respect to a vector. That's generally what you talk about when you say a gradient. If you generalize that, you get a Jacobian. So a Jacobian has a vector in and a vector out. So if we consider an example, a function defined from Rn to Rm. Now both of these are vectors, right? The input is n dimensional, the output is m dimensional, and the input is, let's say, x, which is n dimensional, and the output is y, which is m dimensional. So when we then want to compute the gradient of f at a particular input with respect to x, it's a Jacobian, which is an m cross n matrix. So one thing to remember is that you have the output dimension first and then the input dimension. So m cross n matrix, and you can then write this in the following format. So if you want to get an m cross n matrix, you basically want m rows and n columns, and n columns means that have to then write you'll have to then expand x along the columns. So you can write this whole expression as del y1 by del x1. Then if you keep going on the first row towards the future columns, the remaining columns, you'll get del y1 by del xn. And if you go down, you'll be going across the uh, different dimensions, or the different dimensions of the output. So del y m by del x1 is the last from the first column. So through this operation, you can get an m cross n matrix. So recall this, we were using something similar when we were trying to prove the convexity of certain multivariate functions, or when we were looking at positive semi-definiteness, etc. And once you've discussed the Jacobian and the gradient, we can also now generalize this to what is known as a generalized Jacobian, where the idea is that instead of just a vector in and a vector out, you have a tensor in and a tensor out. So tensor in could mean a dx dimensional input. So something like uh, r n1 cross dot 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 till n dx, and the output y can be a dy dimensional tensor of the shape m1 cross till mdy, right? And then we finally write y as a function of x, and then if you compute del y by del x, it's a generalized Jacobian. Now, this calculation is not as trivial or not as easy to visualize as you did just a minute or two back when you're talking about the Jacobian. So for this, the important thing to note here is that the shapes are still fairly similar. So for the Jacobian, the shape of when you computed the gradient or del y by del x was m cross n. So the shape of the output times the shape of the input. And if you do this for the generalized Jacobian, the shape is m1 cross till mdy, which is the shape of the output times the shape of the input, n1 cross n dx. So that's how generally the generalized Jacobian can be calculated, and we'll be making extensive use of this for doing some of the calculations going forward. Before we come back to the specifics of our backpropagation examples, let's take something really let's take something really trivial. So we can take g as a function of alpha beta, where alpha is a n cross d dimensional matrix, beta is a d cross m dimensional matrix, and if you multiply alpha beta, you'll get an n cross m dimensional G matrix. Right? And we are given the loss as a function of G. So, and let's assume that we already know del L by del G. And just assume that L is a scalar. We know that since it's a loss, it's anyway a scalar. So, we know that the loss has a function of G. And what we want to calculate is the gradient of the loss with respect to alpha and gradient of the loss with respect to beta. So we'll be making extensive use of this particular form, and that's why I'm presenting a trivial example first before we start making use of these in the back propagation case. You might have already seen that where in neural networks does such a form exist. So when you multiply W with A plus B, so W with A multiplication is something like this. And what I'm saying is you've already computed the gradient with respect to the product. So you want to compute the gradient with respect to the individual terms. That's where we'll be making use of what we're discussing now. But before going into any of the specifics, let's discuss this simple case. We want to compute the del L by del alpha and del L by del beta, right? To make matters even simpler, let's just choose some values of n, d, and m to understand better how this uh, this generalized Jacobian computations take place. N equal to 1, d equal to 2, m equal to 3. And then let's write G. Now G is n cross m. So G is a 1 cross 3 dimensional matrix. Let's write G as G1, 1, G1, 2, and G1, 3. Alpha is n cross d, so 1 cross 2. Alpha can be written as alpha 1, 1 and alpha 1, 2. And beta is a 2 cross 3 or d cross m dimensional matrix. So it's beta 1, 1, beta 1, 2, beta 1, 3, and this next row is beta 2, 1, beta 2, 2, beta 2, 3. Right? Now let's just write alpha into beta. So alpha into beta would be now 1 cross 2 times 2 cross 3 dimensional matrix products. So it would be 1 cross 3 as is G, right? So the first row of alpha times the first column of beta, you get alpha 1 1 times beta 1 1 plus alpha 1 2 times beta 2 1. This becomes your first term. Your second term is alpha 1 1 times beta 1 2 plus alpha 1 2 times beta 2 2, and so on and so forth. So you can write alpha beta, and this would be a 1 cross 3 dimensional matrix. Now let's think of how we're going to compute del G by del alpha, right? So alpha is itself now alpha is a vector, right? So one way to do this is to, or the trivial way to do this is to compute the gradient of g with respect to each component of the vector alpha, of sorry, the matrix alpha. In this case, the vector, to make things simpler for us. So we can compute del alpha beta with respect to del alpha 1 1, and for just for the case of, just to make things simple for us, we are just computing them in the same format. So we're not writing alpha currently. So alpha currently is a 1 cross 2, so we're just keeping that it has a one row and two columns. So alpha beta with respect to alpha 1 1, the gradient computation is the, if we compute the gradient with respect to alpha 1 1, we get beta 1 1 for this term. For the second term, we do the computation gradient calculation with respect to alpha 1 1, we get the beta 1 2 term. And for the third term of alpha beta, when we do the gradient computation with respect to alpha 1 1, we get beta 1 3. And similarly, we can do the compute the gradient of alpha beta with respect to alpha 1 comma 2, which was the second term in alpha. And for that, we'll get beta 2 1, beta 2 2, and beta 2 3, right? So we've computed the gradient of alpha beta with respect to alpha 1 1 and alpha 1 2, right? Now if you notice, the shape of del of alpha beta with respect to del of alpha 1 is what? So alpha beta is of the shape, so if you remember the shape of when we were doing generalized Jacobians, we said that the shape of the generalized Jacobian calculated is the shape of what is in the numerator divided by multiplied, so times the shape of the denominator, or the shape of what you're computing with respect, the shape of what is being computed and the shape of what we're computing with respect to. So thus the shape of del alpha beta with respect to del alpha 1 1 is shape of the numerator alpha beta, which is so alpha beta was of the shape 1 cross, let's see, alpha beta is of the shape 1 cross 3, right? Or if we go back, alpha beta is of the shape n cross n, right? And alpha 1 1 is of the shape 1, so it's just a scalar quantity, right? So thus the shape of alpha beta gradient with respect to alpha 1 1 is n cross m cross 1, and similarly for alpha beta with respect to del of alpha 1 2 is n cross m cross 1. So in this trivial case, it seems to be that the shape is actually just n cross m, but in the actual whole tensor, it is of the shape, generalized tensor shape is n cross m cross 1, and not just n cross m, but that one is just trivially ignored in this, in such cases. Okay, so we already know del L by del G. So that's what we started the whole discussion with. We know this term and we want to calculate del L by del alpha and del L by del beta. So del L by del G would be of what shape? L is a scalar, so 1 cross the shape of G, so 1 cross n cross m, right? Since G is n cross m dimensional. And again, we just trivialize this and write this as the following. So since n was 1 and m was 3, right? N was 1 and m was 3. So we can write del L by del G as dg11, dg12, and dg13, n is 1 and m is 3, right? And what I'm now saying is that del L by del alpha can also be written as, since L is a scalar, alpha is a vector of two dimensions, two-dimensional vector. So we can write this as del L by del alpha 1 comma 1 and del L by del alpha 1 comma 2, right? And del L by del alpha 1 comma 1, which is this term, we can write as del L by del G times del G by del alpha 1 1. This is again just the chain rule. This del G, and you can just think of del G getting cancelled, and what you're left with is del L by del alpha 1 1, right? So we already know much of the terms here. We know the del L by del G term, and do we already know del G by del alpha 1 1? Yes, we do that because we calculated that here. So G is the same as alpha beta. So we've already computed del G by del alpha 1 1. Right. So look at the shapes. Del L by del G is, since L is a scalar, 1 cross the shape of G, which is n cross m, and del G by del alpha 1 1. So G is n cross m and alpha 1 1 is 1. So the shapes of these things are 1 cross n cross m, and the second term is n cross m cross 1. And if we just write it out, so we just write these things out. Del L by del G is this term, dg11, dg12, dg13. It's a 1 cross 3 dimensional matrix, and del G by del alpha 1 1, which we computed, was, yeah, beta 1 1, beta 1 2, beta 1 3, right? So this might seem a little odd to you, that you're sort of doing the matrix products of two things of the same dimension. So it's basically, if you see that this thing also appears to be 1 cross 3, and del G by del alpha 1 1 also appears to be 1 row and 3 columns, right? So how do you do matrix multiplication of 1 cross 3 and 1 cross 3? But in essence, this is not the trivial matrix multiplication. This is tensor multiplication, where you have a 1 cross n cross m multiplied by n cross m cross 1 tensor. And since you have both of them of the same shape, what you can then think of it as, it's actually the dot product of these two quantities, of these two vectors. So dot product of del L by del G and del G by del alpha 1 1. If you do that, you'll get a scalar. Does the scalar make sense? Yes, it does, because del L by del alpha 1 1, L is a scalar and alpha 1 1 is also scalar, right? So this thing turns out to be dg11 times beta 11 plus dg12 times beta 12 plus dg13 times beta 13, right? So it's a dot product of the two, which is sort of showing how the matrix or the tensor multiplication in this high dimensional space is happening, right? We can thus just write it more simply. We can just then expand this entire operation and do this again, and then write del L by del alpha equal to del L by del alpha 1 1, and the second column is del L by del alpha 1 2. So this is a scalar, this is a scalar, by the way. So del L by del alpha 1 1 is a scalar, and del L by del alpha 1 2 will also be a scalar. And if you then notice, what is happening is that you basically think of it as, you can write this entire thing, and with respect to the second column also, as, in more simpler sense, as the matrix product of the following. So del L by del G is now a 1 cross n cross m, or when we trivializing this, this is an n cross m dimensional matrix, and beta transpose is m cross d dimensional. And once you multiply these two vectors, or sorry, these two matrices, you'll get a, in the trivial sense, you just ignore that, this one, n cross d dimensional thing, which is what you were also looking at, right? You were looking at an n cross d dimensional thing because that is the dimension of alpha. So this is how the sort of the generalized Jacobians work, and this seems to be again a lot of maths just to get the simple thing, that if you already know the gradient with respect to, if you already know del L by del G, then if you're trying to compute del L by del alpha, it will be of the following format: del L by del G times beta transpose. And in similar lines, we can also compute del L by del beta. And I would highly urge you to do this if you've already followed this particular calculation. And you can see that this will turn out to be alpha transpose times del L by del G. So the good thing now is that we already knew del L by del G, we already know alpha what is, and we already know what is beta. So then we can compute del L by del alpha and del L by del B. So in some sense, we've been able to move even one step further back in a back propagation. Okay, let's come back to our specific example of interest. We had written, okay, so in this specific example of interest, we have already computed del L by del A2 and del L by del Z2. Let's just go back and confirm that we have done this. Right, so del L by del A2 we have written. We have seen how this is computed. Del L by del Z2, we applied chain rule, and we were finally able to get del L by del Z2 is A2 minus Y, right? And then we said that we wanted to compute del L by del W2, right? And we did all of that previous jugglery simply because now Z2 is A1 W2 transpose plus B2, and we want to compute the gradient of Z2 with respect to W2. So it's non-trivial to do this in the case of generalized Jacobians. That's why we resorted to all of that previous simple examples. Let's come back to the same thing again. Alright, so in the generalized setting, we had written G with respect to, so we already knew del L by del G. We similarly here know del L by del Z2, and G was written as alpha and beta. Here we can write Z2 as A1 times W2 transpose, right? So now both of these are equivalent, and we can directly make use of the results which we had obtained earlier to compute the gradient of Z2 with respect to W2 and Z2 with respect to A1. It should be fairly simple to do that now. So first we compute the gradient with respect to beta, right? So beta we have written as W2 transpose, and we have seen that del L by del beta is alpha transpose del L by del G. And if we just write that thing down, so del L by del W2 transpose is alpha transpose A1 transpose times del L by del Z2. Del L by del Z2 we've already calculated to be as A2 minus Y, and A1 transpose we just write it this way. So we can now compute del L by del W2 transpose, but in the gradient computation, so we actually want the gradient with respect to W2 and not with respect to W2 transpose. So we can just take a transpose of this entire term, right, to get what we want. So with it, we take the transpose of this entire term, and we'll get WL by W2, which is now A2 minus Y transpose times A1 transpose, which is just A1. And a good thing you want to do here is to just verify the shapes. So W2 is now N2 cross N1. So del L by del W2 is, in the generalized Jacobian shape, is 1 cross N2 cross N1. A2 and Y both are of the shape N cross N2, where N2 is 1 in this trivial example. So A2 minus Y transpose is thus N2 cross N, and A1 is N cross N1, right? And if you then look at these shapes, so N and N will get cancelled out. You'll get the generalized shape as N2 cross N1 and N2 cross N1. Of course, there is a 1 here also, right? So we have now computed the gradient with respect to W2. Now think for a second and then just write the expression for the gradient of, so del L by del A1. Can you write that using the same formulation that we've been doing thus far? And in fact, so before that, let's try and calculate the gradient with respect to B2. So since W2 and B2 are the parameters of this layer, and A1 would be required for the previous step, as in for the going one step further back. So we want to compute del L with respect to del B2, and we can again apply the chain rule here. So we can basically, even before applying the chain rule, let's just remember what capital B2 was. So let's first, if you remember, we first computed B2 transpose, where B2 is basically the bias terms for all the nodes in layer 2. We take a transpose of that and let's just call it C. So B2 is basically just a repetition of C n times, where n is the number of examples. If you don't remember this, please go back to the discussion where we were discussing about small b, capital B, etc. Okay, once we've written B2 in this particular format, we should then, so in essence we want to compute the gradient with respect to C or with respect to B2. Computing with respect to capital B is as such not required, or is going to be repeated, because C is repeated or B2 transpose is repeated throughout this matrix. All we want is to compute the gradient with respect to one of these rows, which is just B2 transpose, right? So we want to compute del L by del C, and as before we can use the chain rule and write this thing down. And we can also, since C is now what dimension, so C is going to be 1, so C is B2 transpose. B2 is of the shape n2 cross 1 or n2, basically the number of nodes in this layer number 2. So C is of the shape 1 cross n2, right? So del L by del C is 1 cross n2, right? And effectively it's 1 cross n2 if we just trivialize and remove this 1. So del L by del C can be written as del L by del C1 dot 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 till del L by del Cn, and this entire thing is going on for layer number 2. So in fact this particular, okay, this is n2, which del L by del C1, now both of these are scalars. We can further break it down as del L by del Z2, which we already know, and del Z2 with respect to del, so del of Z2 with respect to C1, right? That's basically the term which we now want to compute. Everything else is already there for us. Okay, so let's write Z2 again in a format that can expose basically C for us, right? So Z2 we can write as, it will as Z11, and let's forget about the 2 for now. Let's just assume that we are in, we already know that we are in layer number 2. So Z11 till Z1n2 and Zn till Zn2 n cross n2. So basically you will have the shape of Z is n rows corresponding to n examples and n2 columns corresponding to the n2 features or n2 nodes in that particular layer number 2, right? Which we can write as A2 times W2 transpose plus capital B2, and capital B2 we've just seen can be written as C1, C2 till Cn2, so on and so forth, and this is repeated capital N number of times. So capital N number of times means the number of examples that we have, right? So the only thing which we now need to compute is del Z2 by del C1 for C1, and so the first term here is not a function of C1, so the gradient with respect to C1 for this entire term would be 0. We now need to just compute the gradient with respect to this term, which as you would have seen is, so if you want to compute the gradient of this entire matrix with respect to C1, you element wise compute the gradient with respect to C1, which will turn out to be, since only the first row has C1, remaining rows don't have anything to do with C1, so the first row will turn out to be all ones, right? and this is of the dimension of n cross n2 cross 1. So z2 is of the dimension n cross n2 and c1 is of the dimension 1. So the generalized tensor shape is n cross n2 cross 1. And finally, if we write again del L by del C1, we look at the shapes. So L is 1 is a scalar, Z2 is n cross n2, and Z2 del Z by del C1 when we write, Z2 is n cross n2, and this is 1, right? So finally, when we do this whole computation and just uh, write del L by del C1, we can, okay, so even before that, let's just write del L by del Z2 as, let's assume that we already have it calculated. So we can write this as del Z11 del Z1n 2 and del Zn comma 1 till del Zn comma n2. So again, n rows, n2 columns, n examples, n2 features or n2 nodes in layer number 2, and you're computing the product of this matrix with a matrix where only the first row is ones, right? And on doing so, you'll get finally the summation of I from 1 to capital N times dz1 dzi comma 1, and just forget about the 2 for now. That's it is implicit. This is layer number 2. So I've shown that for C1, I've just shown the specific colors you should note. For C1, you get del Z I comma 1. For C2, this would be dz I comma 2 and so on and so forth. So it's basically just the sum of the respective columns. With respect to C1, when you're calculating, del L by del C1 is the sum of the first column. Del L by del C2 is the sum of the second column of this expression, del L by del Z2, right? And finally, we can write del L by del C as, just write out these individual components, vector components. But finally, just come back and remember that we wanted to compute the gradient with respect to B2 or B and not C. But we already know that del L by del B2 we can write as del L by del C transpose. So finally, when you just compute the transpose of this entire term, you will get an expression which looks like the following. So each row here is a sum of a column in del L by Z2, right? So that's how we can compute del L by del B2. It was fairly involved, but we are almost there. We finally, almost finished the entire back propagation. Okay, so we have thus far obtained del L by del A2 by Z2 by W2 and B2. Now we want to compute with respect to W1 and B1, but we cannot do that till we get with respect to A1, and then we get with respect to Z1. So the same procedure is going to be followed, but let's first calculate del L by del A1, right? To calculate that, we again know that we know del L by del Z2, and we know the expression of Z2 in terms of A1 W2 transpose. So all we need to do is to write del Z2 by del A1, and then we are done basically. Okay, so del L by del A1, we break it down as del L by del Z2 times del Z2 by del A1, and if we go back, this is of the form del L by del Z. So yeah, we we know G, we know del L by del G, and we are trying to compute del G by del alpha, right? So del G by del alpha, sorry, del L by del alpha is what we're trying to compute. Del L by del alpha was del L by del G times beta transpose. So beta is W2 transpose and alpha is A capital 1. So if we finally write del L by del A1, that will turn out to be del L by del Z2 times beta transpose. So beta was W2 transpose the whole, and we take a transpose of that. So del L by del A1 is evaluated as del L by del Z2 times capital W2, right? So almost done with this, and then let's just verify these shapes also. So del L by del A1, this is 1 cross n1, since L is a scalar and A1 is n cross n1, and del L by del Z2 is n cross n2 and W2 is n2 cross n1. Okay, we can go back further and we can then compute del L by del Z1, which is required because we want to update the weights for W1 and B1. So we can write del L by del Z1 as del L by del A1, which is already computed, times del A1 by del Z1, right? Now del L by del A1 we previously computed as del L by del Z2 times W2. We can just write that expression over here, and then we only need to compute del A1 by del Z1, right? Now we've previously done del A2 by del Z2. This is going to be fairly similar to that because the relationship between A2 and Z2 and A1 and Z1 is of the same functional form. It's just that particular sigmoid is applied over that. So if we just repeat what we had done earlier with respect to del A2 with respect to del Z2 and do the just take the lessons from there and apply it on del A1 by del Z1, and we just look at the shapes. So del L by del Z2 multiplied by W2 is of the shape 1 cross, so since L is a scalar, so del L by del Z2 is 1 cross n2, since n cross n2 is the shape of Z2, and multiplied by n2 cross n1, which is the shape of W2, and the shape of del A1 by del Z1 is the shape of A1 is n cross n1 and the shape of Z1 is n cross n1, right? So eventually what we end up doing is to, so just consider the shapes 1 cross n2 cross n2 cross n1. So n2 and n2 in some sense you just assume them to be cancelled. You have terms of n cross n1 and terms of n cross n1. When you end up with the terms of the same dimension, you end up doing a dot product here. So that's the equivalent of the matrix or the tensor multiplication in the high dimension. But whenever you end up with these exact same dimensions, just trivialize it to do a dot product. And when we compute the gradient with respect to del A, when you compute the gradient of A1 with respect to Z1, we just can write as G1 prime as a function of Z1. G1 prime as a function of Z1 we already know, since G1 is sigmoid. So this is going to be G1 Z1 times 1 minus G1 Z1, right? And finally, once we want to compute the gradient of the loss with respect to B1, we repeat the same procedure as we had done previously, and we then again just write del L by del B1 as this particular form. So you sum up the different columns of Z1 and put them as different rows in del L by del B1. So this form is exactly the same as what you've seen before. That is why I'm not showing it here again. So this ends the calculations for a really trivial example that we have seen thus far, where we have fixed the activation function to be sigmoid, and we have looked at only 2 layers, but this entire process is going to be generalizable. Like, you can apply the same procedure for any neural network, but you would have probably realized by now that this is not easy to do by hand. Like, there are a lot of things that can go wrong. Thus it makes sense to apply automatic gradient computation. And let me just show you a notebook which I had created on working out a similar example for the XOR case, and where I had basically written these from scratch. I'm also importing AutoGrad and just showing that the gradient computed by AutoGrad, which is the which is a library for automatically computing the gradients, is exactly matching the gradients which I've computed using the set of formulas that I've written over here in these previous set of slides. I'm trying to solve this for the XOR problem. So my X array looks like 0 0 0 1 1 0 1 1, and my Y ground truth looks like, for 0 0 it's 0, for 0 1 it's 1, for 1 0 it's 1, and for 1 1 it's 0. If you look at the shapes of X and Y, they are 4 comma 2 and 4 comma 1. I'm trying to use the same convention which I've introduced in the slides. So n is the number of examples, which is 4. N0 is the number of input features, which is 2, right? So you can write n comma n0 as x dot shape and n comma n2 as y dot shape, because n2 is the number of layers in the final layer, number of nodes in the final layer. I've defined n1 to be 2, basically saying that the number of nodes in my hidden layer is 2. The first thing which I've done is to just initialize a set of weights. The 0th element is, by the way, just a dummy. I am just using it as a placeholder because I want to use a generalized simple formula. So we'll not be using W0 and B0, but we'll be using W1 and W2, and similarly B1 and B2. This is again just to ensure that we are able to. So uh, I've done this because Python indexing starts from 0, but the computation that we're doing, like we're doing W1, A1, W2 transpose, so on and so forth with respect to those layers. So we don't really do any computation on the W0. So we don't have a W0. I have defined Relu and Sigmoid, and this is basically forward propagation. So you can just write that in 2 lines of code for I in range 1 to length of W. So if you see now, I'm not using W of 0. I am starting from 1. I first calculated Z1, which is A of I minus 1 times Wi transpose plus Bi dot transpose. So sometimes you have to be careful with whether it's Bi or Bi dot transpose depending on the specific implementation that you're using here. And then finally I was just computed AI equal to Relu, or just the activation, and I then computed and confirmed that if A2 is equal to Y with these set of given weights, these are the same set of weights which we confirmed in the previous lecture, which work for Relu. So this is good because I've been able to now show that we've been able to see that using forward propagation we've verified that our Relu network is correct. But now let's come to the learning problem. So I'm going to be using the following shapes. So shapes tells us the number of layers, or basically the n dimensions, right? So the shapes are x dot shape of 1, which is 2, which means that the first A0 is 2-dimensional, A1 is, or Z1 is 2-dimensional, and A2 or Z2 is 1-dimensional. In terms of the activation for the first sort of layer, we don't need an activation. So basically for the input, we don't have an activation. The activation functions, I've just defined a dictionary. For sigmoid, it's a function sigmoid I would have defined somewhere. Yeah, I've defined these functions, sigmoid and Relu. And I've just initialized W and B as before I mentioned. So I don't use W of 0 and B of 0, they're just dummy. This is the forward pass for I in range 1 to length of shapes, Wi Oh, sorry, this is not the forward pass. This is just random initializations. So the shapes of W, as you would have, as we knew, is basically Ni times Ni minus 1. So I just randomly initialize them and similarly randomly initialize Bi's. I have a function which I've created for showing the plots, which we'll come to later. So this is how some plots would look like. Let's see what is right. So make plot takes a function of the iteration and the loss. We'll come to the this plotting function later. We can calculate the objective function. The objective function first computes y hat, and then it's just applying the cross entropy loss, right? So in this for loop, I am computing the y hat going forward propagating. Once I get y hat as a2, I compute the loss as minus y transpose times element wise logarithmic applied over y hat minus 1 minus y. Again, y is a vector, one is while one is a scalar, but Python has this property of NumPy has this property of broadcasting. So this one would be upcasted to a vector of the same dimension as y. We take a transpose of that, apply element wise logarithmic of 1 minus y hat, and I'm just squeezing it to make it a scalar. I'm returning the loss. I'm showing the objective with respect to W and B. So W and B are just randomly initialized for now. The objective with respect to random initialization is 2.99, and eventually over time this objective will become better. As you would expect, I am using AutoGrad and I've imported certain things from AutoGrad. And in this line of code, I'm showing how to compute the gradient of the objective or of the loss with respect to the argument numbers 0 and 1, right? The objective is a function of W and B, right? So basically, when I do grad of objective 0, 1, it means gradient of the objective with respect to W. So here W is the entire W0, W1, W2. I've defined W to be a list where W0 and B1 are useless. W1 and W2 correspond to weights for the first layer and the second layer, and B1 and B2 corresponds to weight for the biases for the first and the second layer. So I've just now written, I've just sort of opened these lists up, and I've shown that if we use AutoGrad and compute the gradient with respect to W1, W2, B1, B2, what do we get? Using the current set of inputs. So the gradient with respect to W2 is calculated by AutoGrad is this two is and is this particular array 0.603 and 0.35, and the gradient with respect to R's, if you remember, let's go back, del L by del W2, right? Let's see what is del L by del W2. Okay, del L by del W2 is, so del L by del Z2 is A2 minus Y, and del L by del W2 is, where is it? Okay, del L by del W2 is A2 minus Y transpose times A1, right? Let's go back to the code. Let's see if this is what we've written. Indeed, that's the formula that I've written. A2 minus Y transpose times A1, and we compared that the gradient of our implementation and the gradient of the implementation of AutoGrad, and we see that they're exactly matching, which came as a huge relief to me that all the calculations that I was doing, all those sort of non-trivial back propagation and multivariate calculus that I was doing, evaluated to the same thing. Again, let's compute the gradient with respect to B2, and our formula said that for B2 the gradient is of this particular format. So I'm looking at the specific columns of uh, Z2 and just summing up these specific columns, and this is exactly what I've written up. So del The del L by del Z2 is A2 minus Y, which I've already shown, and I'm just calculating the sum over the different columns and I'm just reshaping it. And when I compare, I see that we get exact same answer, which is again a huge sigh of relief that what we have done is correct. I've similarly done the gradient calculation for our method with respect to A1, Z1, W1. So these are basically the formulas that we have written in the slides. So for A1 it's A2 minus Y times W2, and Z1 we do an element wise multiplication, so on and so forth, and I do an all close on the set of parameters and their close, which is very satisfying. And finally I've run the gradient descent procedure. I've used a high learning rate. I've used 140 epochs. You could vary these things and change the objective with respect to the number of samples, etc. Just try out those various things. I'm printing every 20 after every 20 iterations. The same thing as I've done earlier. W and B are initialized. W0, B0 are dummy. This is the forward pass. Sorry, this is the initialization. For each iteration, I do a forward pass. I compute y hat. I compute the loss, and I just store that loss. I then compute the gradient with respect to A2, Z2, W2, B2, A1, Z1, W1, B1. So it's a lot of manual effort in terms of computing all of these quantities. And finally, I update WIs with respect to the update rules, which is similar, which is just as simple as WI minus alpha times del WI, and BI is BI minus alpha times del BI. And this is the plot that I get finally after the convergence. So you can see that with the sigmoid activation, one hidden layer, you are able to very accurately classify these examples or draw this get this non-linear boundary. And this is an animation showing the iteration over the convergence over different iterations. Now we started from iteration 0. You can see that initially everything is predicted to be wrong. Gradually there is some of this region which is trying to predict it correctly, then the loss is constantly going down. After some time the loss starts to converge. So with this we'll end today's lecture.